Namaste. Welcome to this channel, Dr.ARM's Chemistry. Friends, we were discussing the crystal field theory, in which we have seen some part of this octahedral crystal field. In this case, today we will see the crystal field stabilization energy. That is CFSE. CFSE, crystal field stabilization energy, that is CFSE. This CFSE measures the magnitude to which the complex is stable. If this value of delta O or crystal field is smaller, it means the complex is not much stable. If the delta value of the complex, means crystal field, is higher, then it indicates that the complex is stable. So the stable complex will not undergo the reactions like substitution reactions, but the complex which is having smaller value of delta, that is crystal field, will easily undergo substitution reactions, in which the ligands, that is weak field ligands, are replaced by strong field ligands. And the ligands, their nature, and the metal ion, their nature, the size, oxidation state, etc., determine the magnitude of crystal field stabilization energy. This stabilization energy can be measured by the absorption spectroscopic methods, where we can find the lambda max of absorption, which is converted into so that gives delta value, and that is then converted into crystal field stabilization energy depending upon the number of electrons which are unpaired or paired. So that will determine the magnitude of crystal field stabilization energy for a given complex. The number of electrons depend upon the atomic number as well as the various levels, that is D level, 3D, 4D, 5D. So as we move in the periodic table from left to right, the number of electrons goes on increasing, and similarly as we also move down the group, in a group, also the number of electrons present in the d orbitals also increase, but the number is same for a specific group. So the total number of electrons increases, but the number of d electrons remains unchanged. So the CFSE is correlated to the number of electrons present in the d orbitals. So we will see how this the electrons are distributed depending upon the crystal field. So we know that the d electrons are ranging from 1 to d1 to d3, and depending upon this we will determine the crystal field and how much or to what degree it is stabilized. So if we see the example of say D1 configuration, then it shows that the crystal field is like this. So these are in octahedral complex. These three degenerate orbitals are labeled as TTG, and these to be generated orbitals are known as EG orbitals. In given configuration, there is only one electron, and so this is the barycenter. So the energy of this P2G is lowered by minus 0.4 delta O, and energy of these EG orbitals is increased by plus 0.6 of delta O. So depending upon this, the crystal field stabilization is also calculated. So for this complex in which there is only one electron in the d orbitals, the distribution of electron is like this. So there is only one electron, so that goes into any of the P2G orbitals. It cannot move into EG orbitals in the ground state. So this is ground state configuration of complex in which the configuration is G1. So in this case, the crystal field stabilization energy is calculated as delta O, and this is number of unpaired electrons 1 into this factor by which the energy is lowered. So that is minus 0.4 delta O, and gives minus 0.4 delta O. This is crystal field stabilization energy for this complex. So we will see the next configuration, that is D2 configuration. So there are these EG orbitals. These are T2G EG orbitals. These are T2G orbitals. And there are 2 electrons present in this. So this is barycenter. So energy of these 2 electrons is lower. Means these 2 electrons, when moving into these lower energy T2G orbitals, will lower the energy of the complex. So we can get this CFSE, crystal field stabilization energy, as that is this value. CFSE is equal to 2 into minus 0.4 delta O. So this gives us minus 0.8 delta O. So with the number, increasing the number of these electrons in the T2G orbitals, the energy of the orbitals or complex is lower. When there is only one electron in the T2G orbitals, it is minus 0.4 delta. When the number of electrons are 2, the energy becomes minus 0.8 delta O. So compared to this single electron, in case of this double electron system, the energy is lower. That is why it is minus. So the negative value indicates that the complex is more stable. So this is less stable, this is more stable, indicated by CFSE. Now, in case of this D3 configuration, we find that there are 3 electrons. So this is barycenter, and we can calculate the CFSE. That number of electrons 3 into minus 0.4 delta O. It gives minus 1.2 delta O. So you can find that with increasing number of electron by 1, the CFSE also lower, and it gives more stability to the complex. Now we will see the next D4 configuration. So these are T2G orbitals. Say these are EG orbitals, and there is barycenter. Now there is barycenter. Here there are two options, because you know that when we can distribute these 3 electrons singly in these orbitals, and there is one more electron. So the question arises that whether that 4th electron will enter here in these any of the 3 orbitals, or it will go into these EG orbitals. Now the possibility of the location of the electron that will go into the orbitals, whether into T2G or EG, depends upon the nature of ligand. If the ligand is weak field, then the situation is different. If the ligand is weak field, means here delta O is smaller. Delta O is smaller. That is, delta O is smaller, and therefore the 4th electron will go into this EG orbital. So for this purpose, the ligand should be weak field. And what are the weak field ligands? The halides, fluorine, chlorine, bromine, iodine, water molecules, OH minus, etc. So in such case, the ligands are weak field, then delta O is small, which makes the movement of the 4th electron easy into the relatively higher energy EG orbitals. So in such case, the crystal field stabilization energy CFSE is calculated as like this: 3 electrons, so 3 into minus 0.4 delta O plus 1 electron, so we take here plus this 1 electron, so 1 into plus 0.6 delta O. So this gives us 1.3, 3 into minus 0.4, so 1.2 plus this 0.6 delta O. So it gives total, it makes the total minus 0.6 delta O. So this is one situation. Now we will remove these other configurations. Now there is another situation where in case of D4 configuration, so these are T2G orbitals and these are EG orbitals. Now here you will find that this is very central. The delta values are same, that is minus 0.4 delta O. This is plus 0.6 delta O. So if ligands are strong field, if ligands are strong field, then delta O is large. Delta O is large, and therefore the electrons are distributed like this. So first the 3 electrons will enter into this T2G. Similarly, 4 electron will also go into this T2G, and therefore we will have this CFSE. What will be the CFSE? All the 4 electrons, that is 4 into minus 0.4 delta O, gives us minus 1.6 delta minus 1.6 delta. So if you compare D4 configuration, there are only 4 electrons, but the difference is ligands are here weak field and here the ligands are strong. So you will find that the value of CFSE is here very small. Minus means lowering of energy. The complex is more stabilized when it gives out energy. So this much amount of energy is given out. That is, energy of this T2G is lower. So the total is comparatively, this is difference is minus 0.4 delta, this is plus 0.6 delta. But by multiplying these electrons with minus 0.4, we get this CFSE minus 1.6 delta. And if the ligands are weak field, delta is already smaller, even though it is also equally large. But this minus the value of CFSE is minus 0.6 delta O. So the difference shows that this is complex. This complex is relatively less stable, and this is more stable. So the difference arises due to the nature of ligands. Here the ligands are weak field, here the ligands are strong. One more difference, that is magnetic characters. This here you will find that this complex is high spin, and therefore it is paramagnetic, more paramagnetic. This is low spin and less paramagnetic, So magnetic characters. So this kind of effect is not seen when the deconfiguration is 1, 2, 3, because there is no effect of ligands, because there are only few ligands which have to enter into the lower energy T2G orbitals. So it makes no difference whether the ligand is strong field or weak field when the deconfiguration is ranging from D1 to D3. But when the configuration becomes D4, then the question arises whether the ligands are weak field or strong field. And depending upon this, the complex will be stabilized by energy, that is CFSE. Then we will see another configuration. Now if you see next configuration, that is D5 configuration, we can have these T2G orbitals and EG orbitals having this very center. So this is very simple. And if we distribute these electrons, so we have to consider whether the ligands are. So we will see the ligands are weak field. Then the electron distribution is like this. The 3 electrons will enter into lower energy T2G orbitals, and remaining 2 electrons will enter into relatively higher energy EG orbitals. So with this, we can find the CFSE. So the CFSE is, we can get this 3 into minus 0.4 delta O plus 2 into 0.6 delta O. So this gives us 3 into minus 0.4 means minus 1.2, and this 2 into 0.6 means plus 1.2. So this minus 1.2 and plus 1.2 makes it 0. So it gives 0 configuration. So delta O is here 0, because this is minus 1.2, this is plus 1.2. So this gives us the configuration where we get this delta O. Now we will take another. So these are T2G orbitals. The very center. Now we will see the ligands. When the ligands are strong filled, then we can place these ligands in this way. So the 5 electrons will enter in this way because the ligands are strong. This energy difference is much larger. Here delta O is small. Here delta O is small, and here delta O is large. This energy difference is large, and this energy difference is small. So in that case, we can have the CFSE. CFSE is equal to 5 electrons into minus 0.4 delta O. So it gives minus 2.0 delta O. So now you can compare here in this liquid complex, all the electrons are unpaired. The CFSE each row. Here you will find that there is only one unpaired electron, 4 electrons in the pair state. The stability is reflected in terms of this CFSE value, that is minus 2.0. So if we compare between these two, this complex is more stable. Again, one more thing is that here you will find that this is high spin complex, on quantization, and this is low spin. Low spin. So this is highly paramagnetic. And this is very low paramagnetic. So magnetic characters are also shown in this way. Now we will see another example. So if we see this D5 configuration, D6 configuration, D6 configuration. So here you will find that the 6th electron will not go into this T2 orbitals. It will come into the lower energy T2 orbitals. In this case, you will find that the 6th electron will enter into this. So here the ligands are strong field, ligands are weak field. Now we can find the crystal field stabilization in CFSE. Here how many electrons are there? 4 into minus 0.4 delta O, and there are 2 electrons, so plus 2 into plus 0.6 delta O. So this will give us 4 into minus 4 means 1 point minus 1.6 delta O plus this 2 into 0.6 means 1.2 delta O. So this gives us how much? Minus 0.4 delta O, that is CFSE. So this is in case of configuration. This is configuration when ligands are weak. Now if we see CFSE here, you will find that there are 6 electrons into low energy T2 orbitals. So 6 into minus 0.4 delta O. There is no electron in each orbitals, so we can have minus 2.4 delta O. So if we compare the CFSE between these two, this is relatively higher energy. No doubt the energy is given out, but comparing shows that this is a relatively higher energy complex, and this is lowest energy complex, that is most stable. So you can say that this is relatively less stable. This is more stable or most stable. Now if we see the paramagnetism, this is paramagnetic. Paramagnetic. This is diamagnetic. This is diamagnetic. This is called a high spin complex. High spin complex. This is no spin, means spin paired complex. This is called a spin paired complex, because all the electrons are in the paired state. So in this way we can differentiate these two types of configurations in octahedral field. Now we will see another example, that is D7 configuration. D7 configuration. So here you will find that the next electron will go here. In this case, there is no place for any more electron in T2G, so the next electron will go here. And in that case, you will find that the CFSE is changing. So what will be the CFSE? How many electrons are there? 5. So 5 into this minus 0.4 plus 2 into same. So it gives how much here? 5 into minus 0.4 means minus 2.0 delta O plus this 1.2. So it gives total minus 0.8 delta O, minus 0.8 delta. Similarly, here we will find that 6 electrons are there, so it gives minus plus 1 electron, 1 into 0.6 delta. So it will be 6 into is minus 2.4 delta O plus is 0.6 delta. So it gives minus 1.8 delta O, minus 1.8 delta. So now if you compare, this is relatively less stable, this is more stable. This is paramagnetic, relatively more paramagnetic, very less paramagnetic, less. Less paramagnetic. So this is more spin pair or low spin complex, low spin complex, and this is the relatively high spin complex. So in this way we can compare between the two configurations. Then if we go to the next configuration, that is D8 configuration. D8 configuration. Now we can have one more electron, so that will go into this T2G orbital, and here it will go into this EG orbital. So in this case, you will find that the ligands are different, but the electronic configuration is same. Now if we calculate the electron CFSE, that is 6 into minus 0.4, and this 2 into 0.6 delta O. So it gives how much? Minus 2.4 plus 1.2. 60 into this minus 0.4, that is giving minus 2.4. So ultimately it will give 1.2 delta O. Now here you will find that the same value. There is no need to calculate. Value is C. So we can directly show that the value is minus 1.2 delta O. The spin state is same. Spin state is same. There are 2 electrons unpaired, 2 electrons unpaired. So both types, even though the ligands are strong or weak, the configuration is same, CFSE is same, everything is same, magnetic characters, spin state, etc. is same. There is no difference. Now if we take another configuration, D9, you will find that the distribution of electron will be like this. Here also same. So here the configuration is same, means everything is same. CFSE is same, spin state is same, then magnetic characters are same. Only one electron is unpaired, so complex is weakly paramagnetic. Now if we see the value, you will find that what is this? 6 into minus 0.4 delta O plus 3 into 0.6 delta O. So how much will we get? Minus 2.4 delta O plus 1.8 delta O. This gives us how much? Minus 0.6 delta O. Same in both cases. Similarly, in case of detailed configuration, the electronic configuration will also be same. So if we see this detailed configuration, so you will have values in both cases. Here 6 into minus 0.4 delta O plus 10th electron will enter here in both cases. Now we will have 6 into this minus 0.4 plus 4 into this 0.6 delta O. So you will find that this will be true. Here it is also the CFSE is 0, same here, no change. So in this way we can differentiate between the stabilities of these various complexes. Depending upon this, we can show that for this purpose we have to remember the spectrochemical series of ligands, in which the initial short ligands are mainly halides and oxygen containing ligands, which are donor atoms like water, OH minus, etc. So these are to be considered as weak field ligands, and the ligands such as NH3 or NO or CO, Cn minus. So such ligands are considered, as shown in the spectrochemical series, are strong field ligands. So we have to remember these ligands, and on that basis we can easily calculate the CFSE for a variety of complexes. So if we consider a few examples, that is say Fe F6 3 minus, then Fe Cn6 Fe 3 minus, then here you will find that this ligand is weak field, this ligand is strong field, and because of this is more stable. This complex is more stable. So on the basis of knowledge about the nature of ligands, we can predict about the stability of the complex. Similarly, we can have many more such complexes. You can consider the COF6, COCl6 similarly complexes, or if we consider COH2O6, COH2O6 3 plus, this is a weak field complex. Weak field, ligand is weak field. The complex is therefore unstable or less stable, we can say. So depending upon the nature of ligands, we can predict whether the complex is stable or not, and that is much better understood by calculating the CFSE, crystal field stabilization index. In addition to this CFSE, further we can also consider the CFSE as net CFSE on the basis of considering the pairing energy. So that will be considered later on wherever it is required. So till then, goodbye, see you next time. If not subscribed to this channel, please subscribe it and press the like button and bell icon. So thank you very much for watching this video.